Ahora no.
Hello, everybody. The next speaker is Leonardo Coito. He is currently doing his PhD here in the University of Valencia and in the UVEG. And I'm going to talk a little bit about him. He is ended his degree in physics in University of La República in Montevideo, in Uruguay. And he's devoted to his research in fields that include the origin of generation of masses in the standard model, and in particular of the Higgs boson and the quark top and active neutrinos. In particular, in the framework of composite scalar bounds state scenarios. He also works in the analysis of methods of dark matter particles to try to explain the relic abundance in the universe nowadays. And is a little bit what he's going to talk to us today. So whatever you want.
Okay. Thank you, Danny. I think this is working, right? Okay. So before I start, I want to thank the organizers for having me. I want to thank you for being here. I'm quite glad that I'm here giving this talk. So the title of the talk is going to be Dark Matter Candidates. What do we know? So I'm going to start. Oops. So I'm going to start to say, what is dark matter, right? Dark matter is basically this idea that new particles are necessary to explain some set of observations that we don't understand very well. So it's not that are not clear for us. And in doing so I'm going to start first section of the first part of this talk by telling you what are these observations. And I'm going to further separate these into two sections. So the first section is about the evidence of gravitational interactions. So this is going to work as if we want proof that dark matter exists. And then a second section, which is no evidence of no gravitational interactions. This will serve like a way to set some properties of the dark matter, as we will see right next. So I want to emphasize before going further that I want you to have this relation between gravity and evidence. So for this talk, I want to point out that gravity will be related to evidence and no gravitational interactions with no evidence, let's say, okay? And the second part of the talk will be about particle physics. So I'm going to start by a brief introduction to the particle content that we know in the universe. This is the standard model of particle physics. And then I'm going to try to introduce you to the need for new particles beyond the standard model. And then talk about a little bit of dark matter. Let's see how the time goes, okay? So let's start. So first part, remember observations. Oops, this goes very fast. Okay, as I mentioned before, there is this set of observations, and this set of observations are showing some discrepancy. This discrepancy is between two things. So on one side is the discrepancy between the visible matter content of the universe that is accessible to us, and on the other side, the framework, the theoretical framework that we know, at least in large scales, which is general relativity. So the disagreement is in between two things. So, so what we will see is that these observations are showing that there is a different curvature of space-time. And this curvature, in Einstein's point of view, we can say that it's related to the existence of a massive object curving extra this space-time, and then we can reproduce the observations. So this is the idea. Remember that we are going to dark matter. So this is the idea that we are going to have in our minds, or we should have in our minds. So in the observations, I'm going to describe you just 5 points, okay? So I'm going to briefly introduce each point now. So the first one is about the rotation of spiral galaxies. So spiral galaxies, these galaxies that have this huge and particular structure as the galaxy that we live in. So in this galaxy, the interesting thing is that there is a different dependence of the velocity of the rotation of the stars with the radius than the one that we would expect. Okay? So let's do a simple exercise. So let's say that we can set ourselves at a radius from the center, okay? And then we could measure, we could like see or try to estimate what is the mass that is inside a sphere that has this radius r, let's say. So how can we do this? Well, actually, we are having the light coming from this object, so we can, this astrophysical object, so we can actually measure, let's say, or estimate what is the mass that is inside this sphere, this sphere. Well, yes. So from that, and using the Newton's law, just to make it simpler, okay, we could estimate what is the dependence of the velocity with the radius. So let's say that for also extra simplifying is, let's say that we can estimate that the mass, depending on the mass of the mass density of the stars as a function of the radius, is approximately constant. This happens actually in some interval of the galaxy, in some galaxies. And so if that's so, we can like equate, right, the gravitational force with the centripetal force, and then we can have a relation of the velocity of rotation with the radius, which is basically saying that should go inversely proportional to the square root of the radius. So we expect in the observations, we should expect that with the radius, we have a quite huge drop in the velocity of rotation with the radius. And this is one of the first observations that came. So here in the y-axis, we have the velocity of rotation of the stars, and here is the radius. So here, and the interesting thing is actually that we are seeing that there is not such a decay in the velocity. So the observation is this curve that is here for this galaxy. So it's actually quite large, even for radius that are quite big. So we are far from the center of the galaxy, and still the velocity is quite fast. It's quite large. So what we can see from this is that, well, actually I can tell you that in this paper, they also plot what they was like this would be this, for example, is the disk. This is the velocity of the disk in the models, only if you think that the stars are inside this sphere, and this would be the velocity distribution if you have the halo of dark matter, let's say, okay, in order to explain this observation. So this is a first attempt to try to explain this observation, and it was giving you these distributions, okay? But the important thing from this observation is that the amount of visible matter is not enough to explain the velocity spectrum in the spiral galaxies, okay? This is the first observation. Okay, now we go to the second one, and it's related to elliptical galaxies. So elliptical galaxies are these galaxies that have kind of an elliptical shape and doesn't have this structure of the spiral galaxies. Are quite simpler. And what happens is that we have the motion of the stars, so we can see the stars and try to, because they have this light coming to us, so we can actually measure what is the speed of these stars, okay, in the galaxy. But also, there is gas that is surrounding these stars, and we expect some correlation between the motion of the star and the gas that is surrounding it. Okay, so astronomers expect there is a correlation. So basically, what they can do is measure the velocity of the star and also measure the velocity of the gas. Okay, so how do they do this? Well, actually, there is X-rays coming from the gas, so they can measure kind of the temperature of the gas. So basically, what you end up is expecting a correlation between the temperature of the gas that is in these galaxies with the velocity of the stars that are surrounding it. Okay, so the first observation was one of the first observations was plotted here, where each point is a galaxy. So well, this was one of the first observations. So don't expect to be a very nice plot with very small error bars. Okay, this was kind of the first observation. So each point is a galaxy, and here the y-axis you have the temperature. This temperature is the temperature I told you. It's actually an average temperature of the temperature that is coming from the observation of the X-rays, okay, from the gas. And in the x-axis, we have this sigma, which this sigma is the standard deviation from the distribution of velocities in the galaxy. Basically, what they are doing is trying to obtain one value for each galaxy. So this is the sigma of the distribution of velocities, and then another value for the temperature, which is basically right. We are relating the speed with the speed of stars, the speed of the gas, and then try to find a correlation. And the astronomers expect the correlation to be in this dashed line. And the observation, at least this observation, was suggesting that the correlation was different. Okay, and the conclusion here was that the gas was actually hotter compared to the speed of the light. So the gas was actually moving faster than it was supposed based on the stars that were there. Okay? Okay, let's go to the third one, the third observation. Actually from here, what you could think is that there is a complex structure or complex structure of density of dark matter inside these spherical galaxies, which is not that easily extrapolated to the spiral galaxies. All right, we are talking about these elliptical galaxies, and there is something else that is actually provoking this increase in the temperature's velocity, this gas velocity. Okay, so the third observation is gravitational lensing. Okay, gravitational lensing is this phenomena that happens when, if we see this figure, we are here, so this is the Earth, and we want to see an object that is here. But in the middle, there is this huge massive object. So here is a galaxy, and the massive object that is between us and the galaxy, our focus, is very massive. So this object is actually curving in space-time, right? And then the light that comes from this galaxy is going to be bent before reaching us. So how do we see this bent light? Well, actually, the light will be distorted in a way similar to this. So here you can have, for example, your cluster of galaxies, like here, you have it here, and then you see the distorted light from this source that is behind, remember, and it's distorted in this way. See, they have these weird angles. This is not real, but it's something that is distorted, okay? And from this distortion, we can actually guess the mass of the object that is distorting the light. And what happens when we are talking about dark matter and discrepancies is that sometimes we don't see the source that is bending the light, and sometimes we see a source, but that source is not enough to actually bend in that way the light, okay? So this is going to help us in the following observation. So for example, the following observation is related, which is in such a way that, so let's say, for example, that we are interested in two clusters of galaxies, one cluster here, and we want to map the density of mass of these clusters. How do we do this? Well, we can do it with weak gravitational lensing. So basically, we can set ourselves in some point, see how the light of objects that are behind these clusters is distorted, okay? And from that distortion, we can guess what is the mass that is there distorting the light. And then we can do the map. So this is what is represented here. So we have cluster, and the interesting thing is that there is a structure of filaments in between the clusters. So there is not just mass in the clusters, dark matter mass in the clusters extra, but it's also in between them. So it's quite interesting. Okay? And now, before going to the last observation, I want to point out something that I said before. So I said before that there is this agreement between two things, right? Our theoretical framework, which is general relativity, and the matter content, the visible matter content that we can reach us, right? And so we can ask ourselves, actually, that maybe general relativity is wrong. And let's say wrong. It has some corrections, at least corrections in the large scale, right? And so physicists work in this other area, right? And this set of theories that they work on are called theories of modified gravity. So I want to tell you that these are like the competitors of the people that believe that there is dark matter. So there are two things that are separated. Some people also work in the mix, but in principle, let's say that there are two opposite ways of explaining the disagreements, okay? So as I said, if we believe that the visible matter content is not enough, we can actually think that there is more, and that's where we are in this talk, so dark matter, okay? And I want to say this for going to the last point. So the last point is the Ballet cluster. So let's go. So the Ballet cluster is a very interesting scenario where we have actually two clusters that are colliding. Okay, so here in this photo of the Ballet cluster, we have here there is a kind of there is a set of galaxies here and another set of galaxies here. And we can see the motion, and they are kind of getting farther apart from each other. Well, farther apart from, the red ones and the blue ones. So this vector is a velocity vector. So what happens here is that we have galaxies from each cluster, and then the cluster just collision. And because the galaxies are kind of point-like in this scenario, if they haven't met another galaxy, they will just cross. They won't see each other. They wouldn't notice the collision. Okay? But the clusters have more than just stars, right? They also have dust and gas, right? So what happens to the gas and dust? Well, actually, they feel the collision, and then we have to go to the next figure, right? So the next figure is showing us the gas, what happened to the gas in this collision. So the gas is in the middle. The gas is represented in the pink color that is coming from the Chandra Observatory. So it's X-rays. So we can see that the gas and the dust is colliding. And the interesting thing, and what makes this scenario so interesting, is that the galaxies that haven't interact has crossed, and the gas that's interacting is in another region. So basically, we can separate what is interacting with other things and the things that are not interacting. So this is a good scenario for testing dark matter. If we think that dark matter is not interacting so much, because actually dark matter could be around us and it's not interacting with us, right? So we say, okay, let's say that there is collisionless, and if it is collisionless, then you wouldn't notice the collision of the two clusters. So what we can do is try to look for weak gravitational lensing in the area surrounding these galaxies, right? Because is what we could do. And then the blue light is actually showing us where is the mass that is bending the light that we cannot see. So basically dark matter in our context, right? So again, dark matter has crossed without interacting, so we are considering non-interacting dark matter, so collisionless. And then we have here dark matter, galaxies, and here the dust. So the interesting thing also is that in these theories, in this scenario, actually it looks like scientists that work on modified gravity have some complications in order to explain the same thing that could be explained much easier with dark matter in the dark matter context. Okay, so sometimes this scenario, the dark matter people sometimes put this scenario saying, okay, we are right and they are wrong, or something like that. But let's say that, at least for this talk, no one is wrong, okay? Two possibilities. Okay, so, so this was the last point that I wanted to make. And the conclusion is kind of that, so we know that the dark matter should have mass, otherwise they wouldn't curve space-time. So we want to know what are the other properties that the dark matter has. So in saying so, we want to look for bounds and guidelines of this matter. And this is where the second section of the first part comes in, which are testing the interaction of dark matter which doesn't involve gravity. Okay? So let's look at... Okay, so basically, this is another way of defining dark matter, basically from the properties. Okay? So here I'm going to point some of the properties of the dark matter. Okay, the first one is that it's neutral, so it doesn't have like fundamental forces. We know that because otherwise, for example, if we interact with a photon, we would have it seen in the skies, right? So the dark matter will avoid these large interactions, so there's like symmetries of the standard models if you want to think about it in a more complex way. So we know that it's neutral, first thing. Second thing is that avoid current detection. So what do we mean by current detections? Well, current detections could be separated, let's say, in three ways, depending on, if we see this diagram, depending on what are the final initial states, what is the current detection that we are talking about. So, for example, these arrows will represent the evolution of the time. So basically, if we will have a scattering, so a dark matter particle interacts with a standard model particle. Okay, think about the standard model particles, the particles that you know. Okay, so if a dark matter particle and a standard model particle interact, and then we also have a dark matter particle and a standard model, so it's scattering, we would say that we are testing direct detection. Okay, so the time goes like this. Okay, in contrast, if we think about the other time, the other arrow, let's say, so we can have, for example, that dark matter is decaying or annihilating into standard model particles. So in this case, we expect to receive standard model particles or particles that you see from sources that are not astrophysical, sources that are not there, basically. Okay? I'm going to talk about more in the following. And then we have, finally, we have also the possibility of have the large hadron, for example, the Large Hadron Collider, where you can test whether the protons produce something else that later produce dark matter and you cannot see in the detectors. So we are actually looking for things that you haven't seen or disappear, basically. So that in that case, you can also test or look for dark matter, right? Is this direction. So standard model annihilation and producing dark matter, okay? If we go to if you think about the direct detection, so for example, I'm gonna just show you an experiment. This experiment, for example, how you test this, if you imagine a lab of this, you have, like, for example, a set of tubes that have some material, in this case, xenon, right? And you're expecting this xenon to be hit, right? The xenon is here in these tubes, and you expect the xenon to be hit by a dark matter particle. So basically hit by something that haven't interacted before and is interacting in that moment. Okay, so basically what happens is that the electron would be a final state, and then the electron would produce photons, and then you could measure. So basically putting these, leaving these tubes of xenon and waiting for the observation is kind of what you do when you are looking for dark matter in the detection, okay? Okay, so I want to point out that we haven't observed so far the detection of dark matter. Actually, we don't have a positive measurement of dark matter. We only know that it has mass because there are discrepancies on the observations. But at the moment of testing on Earth, we haven't seen anything. So for example, here you can see some bounds. So here is the cross-section of nuclei interacting with dark matter. And here is here it says WIMP mass, but let's say it's dark matter mass. Forget about the word WIMPs, it's dark matter. And then you can see, like, there are very strong like bounds on the interaction. So the interaction has to be very small, at least in this range of masses, which is quite big actually. And so the interaction should be like in the white region, right? The other is excluded. Okay? Okay, so now I would go to the third property. So the third property is about lifetime. Okay? And so what happens is that we can bound the lifetime of dark matter basically from two sources. Okay? One of the sources is from this picture that you can see here, that is coming from the knowledge of the particle content that we see and numerical simulation. So basically, you can use the content of matter that you know, use the models of cosmology that you think are true, and then evolve that in time and see whether the structure that you get at the end corresponds to the structure, to the large-scale structure that you see in the universe. Okay? So this will be a representation of this large structure of the universe. So we expect to have that structure when we then include dark matter in our simulations. So when you include dark matter in our simulations with the properties, with some properties, for example, the lifetime, we can check whether we have this structure or not. And this actually sets some bounds on the properties, especially the decay rate, by showing that the lifetime should be larger than 10 times the age of the universe. So actually, the dark matter has to be very stable in order to explain the observations of the universe that we live in, let's say. Okay? And so this is one way of testing or constraining the lifetime, but there is another way, which is indirect detection, the current detection that I just mentioned. So what we are is expecting dark matter to annihilate or decay to standard model particles, and then we look for standard model particles coming from sources that are not astrophysical or were not there. So for example, people is pointing their telescopes or to the center of the galaxy because we expect to be large densities of dark matter, or for example to dwarf spheroidal galaxies like the ones surrounding our galaxy because they have a very nice ratio of signal to background. Basically, they have they have large densities of dark matter and not so many astrophysical sources, so it's nice for testing. Okay, so this is another way of, as I said, having bounds on the lifetime, because if we haven't measured anything, which we haven't, then set of how much the dark matter lives, how much it is stable, right? Okay, so that has to do with the half-life time of the dark matter, and the last one would be that reproduces the Rayleigh abundance. Okay, so basically what we are saying here is that the dark matter should be in in a right abundance in the universe in order to have to explain our observations. What observations? Well, actually, these observations come from two things: our modeling and numerical simulations with the data coming from, for example, COPE, WMAP, or Planck. So from, for example, something like this, that they have mapped the universe, let's say. And so from this type of information is that we have the usual diagram that says that like less than 5% of the energy density in the universe corresponds to visible matter, where dark matter is 25 point something. Actually, the numbers are not updated. I just choose it because the plot was nicer in this way. But so basically, it will be 26 point something, the dark matter density. So that's it, right? The last property is that the dark matter should be in an abundance that satisfies our thinking or knowledge of the universe. Okay, now the second part. I'm going to drink water. 1 second. Okay, for the second part, I told you that I was going to talk about particle physics a little bit, just a little bit. So for that, I'm going to have to introduce you first briefly, because probably you already have the introduction to the standard model in the school. So we know that the standard model has these particle contents, right? So we have the fermions, we have fermions, so this is quarks, leptons, and we have the portal of forces, so these vector bosons, and we have the Higgs, the scalar boson. Okay? And so we can ask ourselves if one of these particles could actually be the dark matter, let's say naively. Okay, so if we take, for example, the up quark, so we know that the up quark have these electroweak interactions with the vector bosons, and also has colors, so it's impossible that the up quark would be a dark matter, right? What we would expect. But still, the question remains: do we know that if there is a particle of the standard model that could be accounting for the disagreement in the observations? So, is there a dark matter candidate among these particles? Well, you could ask, well, what happens to the neutrinos, right? So the neutrinos, we know that they interact very little with everything else. So maybe they are dark matter because we haven't seen them, right? So it could be, we haven't measured the dark matter because it's interacting very little. So maybe the neutrino are these particles, and for some reason we are not measuring them in these detections. Well, actually, there is a kind of a problem with the neutrinos. That is, so a quark cannot be. So, so the problem also that we know that in the standard model context there will be a problem because the neutrinos are massless in the standard model. So, but we know that the neutrinos are massive because we have measured the oscillations, right? So outside of the standard model, thinking about the neutrinos having mass, so we could ask, oh, maybe they are dark matter. Okay, so so here we can ask for that, and the problem is that with the neutrinos is that they are kind of too light, so they have problems because if they are too light, they have at the temperature of the structure formation of the universe, at that temperature the neutrinos will be too fast, right? Because they don't have a large mass, the temperature is quite high for them, so they are actually going faster. If that happens, they scatter the particles of the standard model, and then the structure formation wouldn't happen the way we have modeled. So that's what that tells us, that the neutrinos cannot be actually dark matter because of structure formation. So basically, there are other bounds that I haven't explained here that also excludes you to have dark matter in our models. So when you are doing model building, you have to look for all these details, and not so much details sometimes, that in order to have a good dark matter candidate, right? So basically, that's what we do. So we need a new particle in the standard model, right? And so when we are trying to look for these particles, so if we are trying to do model building, okay, one interesting thing that you can do is to look for portals, so mediators. So let's say that because the dark matter is interacting so little with the standard model, we can think that maybe the interaction is not direct. Maybe the interaction happens through a mediator, and this mediator would be there and would be, for example, having other properties that the dark matter doesn't have. For example, maybe this mediator is much more heavier, So actually, because it's much more heavier, the interactions are very low. This is a little bit complicated, but let's think that way. Or maybe the mediator is actually decaying. So we know that dark matter should be stable, let's say, or 10 times the lifetime should be 10 times the age of the universe. So maybe the mediator actually decays, and you can actually play kind of this game. So there is a mediator, that there is the interaction, the decay, so no problem. So because remember that if it doesn't decay, right, you have to set all these bounds, because then you would see it today, right? But if the decay you wouldn't see today, but it would help you to get the abundance of the dark matter that we know. So the process is a little bit complex, but goes in this direction. So there are some kind of mediators that you can do. So for example, you have to really know how to couple this mediator to a standard model, and there are basically 3 mediators, okay, in some set. And these mediators could be what we call vector mediators. So basically, it's a portal that is vector boson and interacting. So this would be a vector boson that is interacting with a portal portal particle that one of those that we mentioned before. There could be also a portal is a Higgs portal. So basically saying that maybe this mediator, phi, is interacting with the Higgs, and then through the Higgs with the standard model. Or maybe we can say that, wait, there is neutrinos. The neutrinos are being the mediator, so interacting with the dark matter and interacting with the leptons and the Higgs. So this is kind of the 3 ways that we can implement a mediator when we are doing model building and we want a dark matter candidate. Okay. This is what the last things that I wanted to mention. And thank you for attention.
So thank you, Leo, for the talk. If there's any questions, please.
First of all, really nice talk. And I will start by saying I have no background in this topic, but I follow this just for my curiosity. I want to know about this dark matter. As you mentioned in one image, that with the blue color, you just remember, I guess, it showed some color gradients. So I guess, is there any talk about that it condenses itself in density around where there is matter itself, like the standard model particles? Like the particles we have as physically what we see, are they more dense near the...
Maybe I don't know if I am understanding correctly the question. Maybe the question is, is somehow dark matter getting involved in structures like stars of dark matter, etc., compared to the standard model, like the standard model?
No.
Is that no?
No. So as we saw in that image, it showed that near the cluster of the galaxy,
yes,
nearby the cluster,
okay,
showed maybe more density of the dark matter. Of course, we don't know the number of the density, but is there any, theoretical work done or some hypothesis that it condenses itself near the particles or near these physical objects? Is there some talk about that, like it condenses its...
Well, we know that it interacts gravitationally, right? So we should be around these mass, for example, right? Let's say that the universe starts with standard model particles and dark matter particles, and then they will evolve. The thing is that the standard model particles have more interactions, right? So they will tend to gather together faster because they interact more than gravity, than just gravity, right? So we imagine that there is a huge temperature, so particles are really fast. At some point, they will start to slowing down, and then they start the structure formation, no? Starting to get galaxies, etc. But the standard model particles do it faster than the dark matter. So we could expect the stars of dark matter, let's say, but the other ones are created faster. Right, so the dark matter is somehow surrounding it because it has a speed, right? But the interaction are not so large, so they cannot escape, let's say. But this kind of thinking is that the one we are doing.
So the distribution of this dark matter is not homogeneous, as you say, like according to this.
No, it could be
in the universe.
Also you have the clusters. It's surrounding the clusters. Inside the cluster, we know, but also there are filaments in between the clusters. So the structure of the universe is something like this, right?
Yeah.
Oops, like this. Even though No. No, my God.
Dark matter
Okay,
at job.
that one.
Yeah.
So
We
if
can-
I pass faster, maybe you see it.
we saw that. Yeah, so just a thought came when I was listening to you. So is it possible that it condenses itself a lot more near the black holes because it's a very high gravitational object?
No, yes. In principle, yes. I mean, from as far as we know, it has gravitational interaction, so we'll be approaching the objects that are pulling
Yes.
gravitationally. Yes, for sure.
So, like, does
So
it?
they have kinetic energy, and you have to compensate the gravity. Yeah.
So has anyone noticed any dynamic behavior in the density of this dark matter? Like it changes around the black hole, like it interacts much more. Like
I mean, it's an interesting question. I don't know actually.
uh-huh.
But probably it's not so easy in the sense that because you don't see, for
Yeah, of
example,
course.
matter, you see when it goes to the black hole because the velocity is increased and then emits like things, photons,
Yeah,
etc. But dark matter, you couldn't, right? It's
Uh-huh.
maybe it's more complicated. And then you look for other objects,
Okay.
like other sources. So basically, sometimes they look for the whole galaxy or whole center of nucleus of the galaxy. But I'm not an expert exactly in the experimental part, but
I'm
yes, this is
far
more or
from
less
it
my
anyway.
knowledge. Yeah.
Okay. Yeah, it is also just for curiosity, I guess. Yeah. Thanks.
Okay. Anybody else?
No, not him. No, I'm kidding.
What is your favorite dark matter candidate?
My favorite. No, I mean I don't have a favorite dark matter candidate actually. I just been I don't know, proposing many, and then depending on what people like, I'm go for it. Yes. So people dependent.
Okay. I think we have time for 2 questions more.
The question you were raising before, would dark matter be able to form stars, galaxies? What do you think about it?
Well, in principle, it could form other structures, right? If the standard model particles allow it, right? Because they would collapse faster, right? But yes, in principle, you could have large densities of dark matter, and you expect them to be also surrounding the matter of big structures of matter that you see. So that's why basically we look for the nucleus of the galaxy, or those kind of surveys that we do.
Anyone has another question? Okay.
Why xenon for detecting dark matter? You showed us an experiment like the many cylinders with xenon.
Yeah.
And why choosing xenon?
Oh, that's a good question. I remember knowing the answer at some point in my life. I mean, I think I remember that it was either argon or xenon, right? But then, yes, sorry, I don't remember the answer.
Because I found it.
Sorry, maybe Dron, so.
Because they're noble gases, so they're more stable, and in order to detect the scattering with the DM particles, they are
Okay.
the most stable to give the signal. So they are stable and they won't disintegrate into something.
You're saying that because are noble, they
Exactly.
don't
They are
interact.
the heavier, if you go at the last column of the periodic table, you have all
Yeah,
these noble gases, and the heavier ones, as
Yeah.
xenon and argon.
They don't interact very well in
Exactly,
electromagnetic
they don't
way.
interact, but they're stable, and then because they're stable, they also don't interact much with other things.
Okay, thanks.
Yeah, thank you, Dron.
I have a question for you.
Okay.
You
Can it be him? No?
you told that the dark matter you can't see it. Does it means that it is a 0 Kelvin? Because if you have the particles with temperature, it will emit light. So
Sorry,
you
again,
could see it.
please, tell me again, sorry.
You told that we cannot see the dark matter.
Yes,
That means that it doesn't interact with light.
yes.
But does it means that it is 0 Kelvin? Because
Oh, no. Because so temperature is something that depends on. So, for example, these particles could have in some kind of equilibrium between themselves. So you can actually define a temperature for them. That this temperature, they could be actually for having the abundance that we see nowadays. There are many ways for you to reach that amount of dark matter. So basically, depending on whether these dark matter were in equilibrium with the standard model or not, for how long, these kind of things. So if they are in equilibrium with the standard model, we know that they have the same temperature with the standard model. But at some point, they could evolve differently. So yes, so dark matter could have many particles, maybe many particles constitute the dark matter, and they can be interacting with themselves strongly compared to the standard model, so you could define a temperature.
Okay, so thank you for the talk. We can move to the next one. And
Thank you. Thank you again.
is Juan Palacios Gonzalez, and he's going to talk a little bit of physics behind the KEM 3 net and the neutrino telescope.
Okay, now, no? Yes, now. Okay. So, hello everyone. It's a pleasure to be here in this school. I'm Juan Palacios. I'm a predoctoral researcher at UVEG, and today, as Danny said, I'm going to tell you about the physics behind the neutrino telescope, and in particular, KEM 3 net. So let's start by the very beginning. Oh yes, it's sensitive. What is a neutrino? No, I know that you already had a very nice talk by Maria about this topic, and Leo also mentioned the neutrino. No, so you already know that neutrinos are the closest thing to a ghost that we have in particle physics. They are elementary particles, so they don't have internal structure. Actually, you can see them here in the standard model. We have 3 types of neutrino, or 3 flavors of neutrinos. They don't have electric charge, so they cannot feel the electromagnetic interaction. And they don't have color charge, so they cannot feel the strong force. We know that they have mass, but we don't know the value of this mass, but in any case, we know that they are very light particles. This mass is several orders of magnitude below the mass of the electron. Okay? So in any case, gravity is a negligible interaction. So this leaves us only with the weak force as the only interaction that neutrino effectively feel, okay? And that is the reason why they are very difficult to detect. Not impossible, but very difficult, okay? Because as the name indicates, it's a very weak interaction, okay? The neutrino is the second most abundant particle in the universe, just after the photon. Actually, if we put our hand like this, tens of billions of neutrinos are passing through our hand every second, just as if our hand were not here, doing nothing with our hand, not interacting with us, okay? These neutrinos are mainly coming from the sun, but the sun is not the only place that produces neutrino, okay? Neutrinos produces in many nuclear reactions. You can take a look here, no? The sun, the Earth itself produces neutrino. In the atmosphere, neutrinos are produced. Even our body produces neutrino, no? In nuclear reactors, of course, there are nuclear reactions, so neutrinos are produced. And in particular, in my research, we are interested in a very particular kind of neutrino that are what we call the cosmic neutrinos. Neutrinos that are coming from beyond the solar system, from the universe itself, okay? We know that this cosmic neutrino exists, but so far, and this is an open question nowadays, we don't know which kind of sources are producing these neutrinos, okay? But cosmic neutrinos are really interesting because they are we can put in what we call the neutrino astronomy, no? They are a new window to the universe. The thing is that you know that so far up to now we have seen the universe with the light, with the electromagnetic spectrum. This is with the photon, no? this is good because the photon is very easy to detect, okay? But the thing is that the photon, the light interacts a lot with the matter, okay? So if you have a given source that produces these photons and you have a very light glow of matter between the source and the Earth, you don't know if the photon may interact with this particle that can be in the middle, no, this cloud. So they can be photons can be absorbed and re-emitted, and this can change the direction, no? So this is something that we don't know. We want to know exactly where is the source, no? There are other particles that you can take a look to, no? For example, we have what we call the cosmic rays, which are charged particles at the end of mainly protons, okay? But the thing with the protons is that you know they are a charged particle, no? And there are magnetic fields in the galaxy. So as charged particles, they are going to be deflected by this magnetic field, and you are no longer going to know where is exactly your source. This is something that do not happen with the neutrinos, because they don't have electric charge, and they interact very little with matter. So they are going to come directly from the source in a straight line. But now the challenge, this is the good thing and the bad thing, because now the challenge is to see the neutrino here in the Earth, okay, to detect them here. I just want to briefly mention that this neutrino astronomy has to be understood in a multi-messenger context. Each messenger has its own advantage and disadvantage, okay? And we want to put in common all the information that the different messengers are giving us. The photon, the proton, the neutrino, and also the gravitational waves, okay? That you may know them. So now that you know better the neutrinos, you may ask me, okay, but why do we really want to detect these neutrinos, no? One thing, the first reason we already explained it, no, for the neutrino astronomy, to see the universe with a new eyes, no? But there are more reasons. As I told you, we don't know still the mass of the neutrino, no? At the end of the day, neutrinos is an elementary particle. So if we really want to understand the universe as it is, we need to understand the neutrino, no? So knowing the mass of the neutrino is something that we really want to do, no? And also knowing the properties of the neutrino, because you may know that neutrinos have a very particular thing that it's called the neutrino oscillation. The neutrino is able to change from one flavor to another. And this is a quantum effect that has only been seen in the neutrinos, okay? So understanding this effect is something that it's understanding at the end of the day the nature, no? So it's interesting because of that thing. And also, because of that matter, no? Leo already explained you that there is a way which is called the indirect detection, no? If we detect neutrino, we may infer if there are structures in the universe of this dark matter, no? So there are several reasons. But okay, now that we really know that neutrinos are interesting, how do we do it? How do we really detect this tiny particle, no? I'm going to give you a very simple recipe, okay? The first thing that you need is to use a large detector. If my detector is very big, it will be more likely that at some point of the detector, I will see a signal coming from the neutrino than if I use a small one. No? It's logical. This already gives you a clue of the reason why we go to the sea to put the detector, okay? Because it's a very big mass of matter, transparent, that it's already there, okay? It's cheap. And the second thing that you need to have is to have patience. Because at the end of the day, detecting neutrinos is a statistical issue. The longer you wait, the most likely is that at the end you see a signal from the neutrino, okay? And you accumulate this statistic. But let's go into the physics. How do we really do it? How do we really detect neutrino with the neutrino telescope? So let's consider that we have a given source in the universe. I don't know, an active galactic nuclei, okay? And this source is going to emit a neutrino. This neutrino will travel from the source to the Earth here, and it will arrive, in this case, to the Mediterranean Sea, okay, to the Mediterranean Sea. And we are going to consider that this particular neutrino is going to interact, okay? What we mean by interaction is that some new particles are going to appear. And this new particle, in this case, it's going to be a muon. The muon is some kind of cousin of the electron, okay? Like a big electron, let's say. It's another elementary particle, okay? With more mass. So the thing now is that this muon is so energetic, because the neutrino was so energetic, that this muon is going to travel faster than the speed of the light in water. And this may call your attention. You can tell me, hey, we know that Einstein said that nothing can go faster than the light. And it's true. But that is in the vacuum. In the material medium, the speed of the light is lower than the one of the vacuum. And if a particle is sufficiently energetic, it can overcome this threshold going faster than the speed of the light in this particular medium. No? And when that happens, there is a very curious effect that it's appear a cone of what is called a blue cone, a very characteristic blue cone, which is called the Cherenkov effect. Okay, it's what happens when this source is moving faster than the speed of the light in the medium in which it's moving. It's some kind of interference, constructive interference. Okay, so the thing actually you can see it here. For example, when a nuclear reactor is on. Okay, you see this very characteristic blue line. It's exactly the same. These are two very different things, two very different examples, okay? But the physics behind is exactly the same, the Cherenkov effect, okay? So let's summary. As a result of the neutrino interaction, we have a cone of a very characteristic light, a cone of the blue Cherenkov light. And this is cool, because the neutrino itself, we cannot see it. But light is very easy to detect. So if we now place a detector in the very bottom of the sea that will see the different parts of the cone, we will detect the Cherenkov cone, reconstruct the track of the particle that was born in the interaction, and therefore infer information about the neutrino that interacts, and what is more interesting, the source that produces that neutrino. Okay? This idea is something that you can see in this video here. Here we have the cosmic neutrino. Of course, it's not green, it's just here so that we can see it. This cosmic neutrino arrives to the Earth, as you can see, okay, to the Mediterranean Sea, and it's going to interact. There you see the interaction, and appear this cone of the Cherenkov effect that I already explained you, okay? So now we have ready there our detector, so we can see different parts of the cone. We detect the cone, we reconstruct the track, and we infer information about the neutrino, okay? And that's the way we do it. So this idea that I already explained you, it's already a reality, has already been done. Here you can see a cartoon of the very first generation underwater neutrino telescope. Its name is Antares. It's located in the Mediterranean Sea, in the shore of France, and it consists of 12 lines, 12 strings, which are ubicated at the very bottom of the Mediterranean Sea, at a depth of 2.5 kilometers. Okay? It has been taking data during 16 years up to this very year, and the way in which they detect the cone is through this structure here, the cone of Cherenkov light, I mean, which is this one here that you can see. No? This is an optical module which has a photomultiplier embedded. The photomultiplier is the device that we use to detect light. Okay? So we have several structures, and that's the way it can see the cone of the Cherenkov light. You can see here some pictures of the deployment of Antares back in 28, and you can see here this picture which was taken actually a few months ago of the recovery of Antares, because Antares has been switched off. We have already stopped taking data with Antares, because now we are building the second generation, sorry, okay, here. The second generation neutrino telescope, the cubic kilometer neutrinos telescope, CAME3net. You can see that it's a more modern design, okay? Instead of one very big photomultiplier, we have several small photomultipliers looking at different directions. So this design helps to detect better, let's say, this cone of the Cherenkov light, okay? Actually, we are building two detectors with the very same technology, but two different detectors. One we call it Orca, which is for a smaller one, but compared with the other one, I mean, by small. So this is for low energy around the giga electron volt, and it will study these fundamental properties of the neutrino, not this open question of the mass and the neutrino oscillation. This is what Orca wants to detect, wants to study. And the other high energy array that you can see here is ARCA for higher energy, from the sub-tera electron volt up to the few peta electron volt. And this is mainly focused to the astrophysical study. No, both are in the Mediterranean Sea. Orca is close to Antares, close to the shore of France, and ARCA is close to the shore of Sicilia. Okay, and here you can see the way in which we deploy this line. It's really a challenge. No? You can see that we have these spherical structures where we embed the line. Okay, and now we'll allow this spherical structure to sink in the water until the very bottom of the Mediterranean Sea. It takes several hours, okay, to arrive to the bottom, as you can see in this video here, no? And once it's hitting the bottom, we allowed it, the spherical structure to unroll, to unfold, okay? So that it deploys the string, deploys the line. So actually these two pictures here, these two, were taken just 2 weeks ago. Because as I'm telling you, we are already right now building these neutrino telescope, these detectors, okay? So once we arrive to the very bottom of the sea, this is what you can see. This is a real picture from the bottom of the Mediterranean Sea, no? And this is what I'm telling you. Wait. What is going on? Okay, seems doesn't work. Oh, there it is, okay? This is what I was telling you. This is the unroll, okay, of the structure deploying the line ready to detect neutrino, no? So at this very moment, ORCA counts with 10 lines and ARCA counts with 19 lines, but we are still growing. And the nice thing is that we are already taking data. We don't need to wait to the detector to be completed to start the data taking. We are already taking data, okay? Of course, once the detector is completed, we will have more sensitivity than the one that we have now. The sensitivity is the way in which we can differentiate the signal, which are the neutrinos, from the background, which is what is not a neutrino, okay? But yeah, that's the nice thing, that we are already taking data. So, just to conclude, the take-home message that I want you to learn from this talk is that we know that cosmic neutrinos exist, but so far we don't know which kind of sources are producing them, okay? So keep an eye on the result that Chem3D will give in the next few years, because I really think that this detector has a lot to say about this respect. So that's it. This is a group of our picture here, of our group here at IFIC. Our name is Vega. We are part of Chem3D. Chem3D is an international collaboration. Several countries, several research groups participate together in the construction of the detector, and we are part of the collaboration. So if you want to keep an eye on what we are doing and how we are building our detector, you can follow up on our social media here. And that's all from my side. Thank you so much for everything.
Thank you for the talk. If there's any questions.
Okay, thank you for your talk. It's very interesting. It has been very interesting. So I have a question about the noise, because of course you are detecting things, but then you can you should be able to say that this comes from a neutrino and not from another thing. So can you tell us something?
Indeed. About the background, we call it the the noise at the end of the day. Exactly. That's a very good point. Indeed, I have here some slide. Wait me a second. Yeah. The thing is that the way I explained you, we detect the neutrino. This signal, this cone of Cherenkov light, are not only produced only by neutrino, as you very well point. For example, these muons that I mentioned also come from the atmosphere. It's what they are producing in the atmosphere, and directly from the atmosphere they come and they give signal in our detector. We can see them, okay? So, and this is not a neutrino, it's something different. So, yeah, indeed, that's actually what I'm working in. To try, at the end, it's a statistical analysis. You have to, depending on the kind of signal that they are producing, you will be able to see if it's a neutrino or not. For example, imagine if you see this one coming from, this is what we call upgoing. No? The atmosphere, it will be here, and here you have the Earth, okay? So if you have a signal coming from downgoing, it's going to be very likely that it's a muon, an atmospheric muon, because it's coming this way. But if you have a signal that is coming upgoing directly from the Earth, it has a probability of being more probability to be a neutrino, okay? Because muon cannot go through the Earth. The neutrino can, because as I told you, neutrino don't care about matter. So the neutrino go through the Earth and there is no problem, but the muon cannot, okay? So at the end, it's a statistical analysis. We don't look only at that. No, we look at a lot of variables of the reconstruction of the cone. Let's say at the end it's what we call the event selection. You choose the sample of events that they have a high probability of being neutrinos, cosmic neutrinos, because also the problem here with ARCA, in the case of ARCA, is that you can see also the atmospheric neutrino. Remember, the atmosphere produces neutrino, and you can see them, but we want to see the cosmic one in the case of ARCA, not the atmospheric. So for us, atmospheric neutrinos are background in the case of ARCA. So we want also to reject them, because we want the cosmic, you know. So that's it, thank you.
Well, thank you for your talk, Juan. I have a question. Unfortunately, we have there are a lot of open questions in neutrino physics, and I wanted to know that, well, from your experimental point of view, which is the closest to be solved, or which is the one that you are more confident to?
I'm
Just curiosity.
the thing that I think that we will see soon, or
For instance, are we planning to determine their nature, whether they are Dirac or Majorana particles, or their mass hierarchy?
yeah, I'm
What do you
not an expert in that part. This is more belongs more to the theoretical one. So I'm more focused in the part of the experimental. I would say for me, and what I really think that chem3net can help a lot, and the other, because there are other neutrino telescopes, what I think that they can contribute more is to understand the origin of the cosmic neutrinos, where they are coming. I think I really hope that we are close to that point. In the next, I don't know, decade, 2 decades, I think there are questions that may be solved. Because as I told you, we already know that there is what we call a diffuse flux of cosmic neutrino. Diffuse in the sense that it's there, it has been detected by another experiment that it's called IceCube. I have it here. IceCube is the same, exactly the same thing, okay? Here is chem3net. We are in the Mediterranean Sea, but IceCube is another one that is in the sea. With the same, they see also the Cherenkov light, but instead of seawater, they do in ice, okay? And they are the one who detected this cosmic diffuse flux that I told you, no? So now the challenge is to match these neutrinos to the source that we know that they are there because of their experiment, because gamma ray experiment, because X-ray experiment, and all these things. So I really think that will be, I hope that will be achieved in the next years. But let's see.
Hello. Thank you for the talk. Very nice. So the range of energies of the neutrinos, the cosmic neutrinos, is different from the range of energies of the atmospheric neutrinos?
Very good. Yeah. For sure. Actually, we expect the one of the cosmic neutrinos is higher than the one of the range. That's why we need ARCA, because ARCA, as I show you here it's work. This is ORCA, oscillation reserved with cosmic in the abyss, and this is ARCA, astroparticle reserved with cosmic in the abyss. Okay, so ARCA covers energy from the sub-tera electron volt to the few-peta electron volt. They can see atmospheric neutrinos at the low energies, but when you see an event with, I don't know, with this and with hundreds of tera electron volt, it's very likely that it's coming from the cosmic. This is something also that allows to discriminate. No, the variable that I mentioned before, the energy is actually one of them. Indeed, when IceCube discovered this diffuse flux of atmospheric neutrino, it was in 2013, and they detected 28 high energy events, so energetic that there was no chance for them. In principle, there is a statistical analysis behind, okay? But in short words, there was no chance for them to be produced in the atmosphere. They were so energetic that they were coming from beyond the solar system, okay? From the universe itself. So that's it.
Okay, so thank you again for the talk, and we can move to the next.
Thank you.
Okay, so the next talk is gonna be by Jorn. Sorry for my pronunciation.
Yeah.
And he's going to talk about the matter-antimatter asymmetry of the universe. And it's the stuff that I'm studying too, so I hope you enjoyed his talk.
So do we have this pointer here which works?
The pointer is this.
Okay. Perfect. Okay, all right, good afternoon. I am Dron, and I'm also a pre-doctoral researcher at Institute of the Física Corpuscular.
And today I'm going to be talking about the matter-antimatter asymmetry of the universe. So far we've had two talks. The first one by Leonardo that you saw, which was on dark matter, by Juan on neutrinos. And the third one, this is the matter-antimatter asymmetry. Together, these three problems, the dark matter, neutrinos, and this asymmetry, they're some of the challenges that the standard model faces right now. So in this talk, I'll be very brief. It's a short talk. The idea is to just give you an introduction as to what this matter-antimatter asymmetry is, what mechanisms there could be for this, and just motivate you enough. Okay, so what's going on exactly? All right, so moving on. Okay, what is matter? We don't have to talk about this because you are too advanced for that. So what is antimatter? Right? So everything that we see around us is made of matter. We all know that. But where is antimatter? What is antimatter? Is it the stuff of science fiction? If you've seen this movie, Angels and Demons, or if you read the book, you know that this protagonist, Robert Langdon, he's trying to save the world from an antimatter bomb. So you must have seen there. If you know about Star Trek, so their jets are basically fueled by antimatter fuel. But okay, it's not the stuff of, it is the stuff of science fiction, but we are here to do physics, so I'll go next. What is antimatter? So these are identical to their matter counterparts. By that, I mean they have the same mass, but they have opposite properties like opposite charge and spin. For example, we know that the electron is negatively charged, so the corresponding antiparticle, which is the positron, has a positive charge. So similarly, you know, like the electron and the proton form the hydrogen atom, you could have an anti-hydrogen atom, that would be the antimatter. Over here, I've put pictures of three important people, one who coined the term antimatter, Dirac, who gave the theory of antimatter, and Carl Anderson, who discovered positron. And that's how we detected the first antimatter. Anyway, so this is what antimatter is. And, okay, right. So you must have grown tired of seeing this picture so many times throughout the day, but you only saw half of it, okay? So you only saw the half part. You were seeing this part and this part. But in reality, it's much bigger because for each particle, you have an antiparticle. I mean, for most of them, yeah. So which have the charges. I mean, even the neutrinos, they have charges. They're neutral, but they have a corresponding antiparticle because I said that there could be other properties also which are different. So this is the big standard model. Over here we have quarks and leptons. Quarks together, three quarks come together to form baryons. A quark and an antiquark pair combine together to form mesons. Examples of baryons are protons and neutrons that form the nucleus. So I'm telling you this because I will use the terminology of baryons and mesons later. Okay, so this is the standard model of particle physics, and okay, this is the complete picture. Now, what happens when matter and antimatter meet? So as this picture is quite descriptive, what happens is when a matter comes in contact with antimatter, they annihilate together to produce huge amounts of energy. So basically the process is like this. So you have an electron and a positron coming in together, they annihilate, producing a lot of energy which is basically taken in the form of gamma rays. On the contrary, you can also have processes where like there is energy and you can have matter-antimatter pairs popping out. So energy coming in together and producing matter-antimatter pairs. So this idea comes from the famous equation of Einstein, which equates energy to mass. So you know you have energy and you can produce two particles. So the first one is called pair production, and the second one is called annihilation. The important thing is that when they meet, they produce huge amounts of energy. For example, if I had 1 gram of antimatter, if it comes in contact with matter, it will produce an explosion that is equivalent to a nuclear bomb. So you can understand, so you get an idea of how big this explosion is. And that's why Robert Langdon was trying to save it, because somehow they stole some antimatter from laboratories of CERN and they wanted to destroy something. But in reality, the amount of antimatter that we have produced in these experiments at CERN or Fermilab, it's of nanogram. So if you put it all together,
it wouldn't have enough energy to boil a cup of tea. So this is the amount of antimatter we have, or we have produced. So that's why that was science fiction. You cannot make antimatter bombs because we don't have that many antimatter. Okay. So coming on. Okay, so we know there is antimatter. Antimatter exists, but where do we find it? So the first one, these are cosmic rays. So there are antiparticles or antimatter, I'll use it interchangeably. They're getting showered down on us constantly in the form of these cosmic rays. The second one is lightning, thunderstorms. During this also, you have like pair production, and you can have some antimatter particles being produced. And the third one is a banana, because the banana contains this radioactive isotope called potassium-40, K40, and which produces antimatter. But all in all, so if there is antimatter which is being produced, which is there, we don't see these annihilations happening, at observable scales, As I said, okay, they meet, they should explode, they should produce a lot of energy, but we are not seeing these things. This is very rare. What it tells is that the antimatter is present in really, really small quantities. So it's rare. And second, since it annihilates immediately when it comes in contact with matter, it is also very short-lived. Okay? So this brings me to the most important question. What if antimatter wasn't so rare, Okay, let me rephrase this. What if antimatter was present in equal amounts as matter? What would happen? We wouldn't exist, right? There would be just nothing, because all the matter would annihilate with all the antimatter. At the end, there would be nothing, just filled with energy. But we do exist, so sadly, or not so sadly. And that is attributed to what the physics term is the baryon asymmetry of the universe. So the matter-antimatter asymmetry is a very generic thing that I titled my talk. But when you do physics, particle physics, you call this thing as the baryon asymmetry of the universe. Now, what we believe, as per our theory of the Big Bang, that the Big Bang should have created equal amounts of matter and antimatter in the early universe. Okay? So, as I showed you, as I showed you about the pair production, so there was this Big Bang, everything was super hot, super energetic, so there were pairs of matter and antiparticle being produced. They were popping in and out of existence. They were coming in, annihilating, being produced, and so and so. So we say that universe started in a symmetric state. But then something happened. What happened was that at the end, this is roughly 10 to the power minus 9 to 10 to the power minus 6 seconds after the Big Bang, what happened was that there was one extra matter particle for every 10 billion matter-antimatter pairs. So if there are 10 billion antiparticles, I had 10 billion and one particle. So this ratio, this asymmetry of the order 10 power minus 10, this is the observed baryon asymmetry of the universe. And this is how asymmetric the universe is. Now, here you can ask me, what if I relax this assumption? What if I say that the universe did not start in a symmetric state? What if the universe started in an asymmetric state? What if this asymmetry was built in as an initial condition and not something that was generated dynamically later? Well, if this would have been the case, to produce this tiny, this is of the order of 10 power minus 10, requires a lot of fine-tuning. Like it had to be really, really fine-tuned so that the asymmetry came out to be of the order of 10 power minus 10. And in physics, we don't like fine-tuning. We don't want to do fine-tuning because it makes our models look ugly. So that's why we do not, that's why we believe that this wouldn't have been the case. The second bit is, what if the universe is still symmetric and there are regions of antimatter maybe in some other universe, whatever, say multiverse or whatever. There are regions made entirely out of antimatter, whereas our visible universe is just made of matter. If this was the case, at the junction where our universe would meet the other regions of antimatter, at the border, the matter and antimatter should meet and produce a lot of collision. I mean, there will be a lot of annihilations and a lot of gamma rays, as I showed earlier. And if this would have been the case, this excess flux would have been observed by our experiments. But we haven't observed any of those fluxes. So that means that, okay, right now we believe that, okay, it means that, yeah, the universe is asymmetric. We have things entirely made out of matter, and there might not be regions made out of antimatter. I will come back to this point later in the talk, okay? But right now, we say universe started in a symmetric state. Something happened. There was some mechanism at play, because of which, at the end, there was one extra matter particle for every 10 billion particle-antiparticle pairs. Okay. So the question is, if the universe started in a symmetric state, what tipped off the balance? I just posted this picture here because it looks cool. Big Bang, you start at Big Bang, things are symmetric. You see at the order between 10 to the power minus 30 to 10 to the power 1, you have particles forming. So before this, in this region over here, all the matter-antimatter annihilation should have taken place, and only particles should have been left, and then the formation takes place. So what tipped off the balance? So there was some mechanism that was present in the very early universe, which dynamically led to the excess of baryons over antibaryons. And we call this dynamic generation of asymmetry as baryogenesis. Okay? Now, in order to realize baryogenesis, if you want to do baryogenesis, there are these three conditions that you need to satisfy, which are named after this Soviet physicist, Andrei Sakharov, who won a Nobel in Peace, by the way, because he was also against violence and arms and stuff. Anyway, so the three conditions are baryon number violation. Remember, I was talking how three quarks come in together to form a baryon when I was giving you the whole picture of standard model. So we have baryon number violation, we have C and CP violation, and we have departure from thermal equilibrium. I'm going to go to each of these points one by one to tell you what exactly it means. Okay, so the first one is baryon number and its violation. So baryon number is basically an additive quantum number, which is simply given as 1 by 3, where these are the number of quarks and antiquarks. For example, in proton, you have 2 up quarks and 1 down quark. If each of them have baryon number 1 by 3, so the baryon number of proton is 1. Neutron is UDD 1. So baryon number is one of the accidental symmetries in the standard model, which is conserved for all processes. I mean, at least we haven't observed baryon number violation. So in order to first, in order to generate an asymmetry, we need interactions that do not conserve this number. Because if all the interactions conserve baryon number, then we won't be able to increase or decrease the baryon number. That's why we need presence of interactions where the baryon number is not conserved. So that by violation, I mean that B initial should not be equal to B final. So this is the first point, that the baryon number should be violated. The second part was charge parity symmetry and its violation. So CP asymmetry is basically charge parity asymmetry. It's a combination of two discrete symmetries called charge conjugation and parity. Now, from this schematic diagram that's over here, I show is what charge conjugation does is flipping the charge, as the name suggests. Positive becomes negative, negative becomes positive, and so on. About parity, parity flips the handedness. This is like what you do when you see yourself in a mirror. Your left hand becomes your right hand becomes your left hand. So this is a simple way of saying, okay, this is what parity does. So initially it was believed that all these symmetries were preserved, like C was preserved, P was preserved, and the combination of C and P was also preserved, like these are the symmetries. But what we found was that C is violated, P is violated, and we were very hopeful that CP is still preserved, but in 1964, we found that CP is also violated. And this is good for us. And I'll tell you why this is good for us. Because if CP symmetry is conserved, it means that nature treats particles and antiparticles on an equal footing. You know, they are the same. It treats it treats particle and antiparticle alike. So we need this violation because we need to be biased. We have to be more biased towards the particle than the antiparticle, and that's why we need CP violation. What by CP violation? Let's say what I write here is that when you say CP conserve, let's say if you have a decay of a particle A going to B, the same, okay, there should be a bar over here. The same is true for the reverse, for the antiparticle conjugate, that it should be equal to A bar going to B bar. But when there is CP violation, the rates are not the same. It prefers decaying to the particle more than the antiparticle. So this is CP violation. And the third point, the third Sakharov condition was the departure from thermal equilibrium. So, you all know what equilibrium is. You know about thermal equilibrium, chemical equilibrium, and so on. What it means is that processes can go both in forward and backward direction. But to generate an asymmetry, we need some out of equilibrium dynamics, because let's say I create the asymmetry, but then the reverse process can wash out that asymmetry. So somehow these processes should go out of equilibrium, so what I go in forward direction does not come back in the backward direction in a very naive way. So that's the out of equilibrium condition that we need as the final ingredient to dynamically generate an asymmetry. Okay, so let's look at the recipe. So far what I have talked about. Again, just a representation. So let's say we started initially in a symmetric state. So my asymmetry parameter eta is 0. I have equal amounts of B and B bar. Then this mechanism has come into play. And it starts decaying, let's say, more into B than B bar. And it produces an axis of B over B bar. And now it's asymmetric. In the third part, what happens is that the symmetric component, okay, of course this is equal, this part will come together and annihilate. So the symmetric components get annihilated. And at the end, I just have the asymmetric component left. So this is the case. Of course, this is exaggerated, but when I told you about the number, it was 1 in 10 billion. So of course, this difference is not that much. Here it's just for representation purpose. So at the end, we only have the asymmetric component left. So this is the recipe for baryogenesis in a very simple way. Okay, the big thing is that the standard model has all these three ingredients. Yet, so it has baryon number violation, which we haven't observed, but there are some processes which are active in the early universe. These are fast. I mean, in the technical term, they are non-perturbative. So they could be there, so we could get baryon number violation from there. C and CP violation has already been observed in the standard model. For example, as I showed, that the CP violation was detected in 1964 by those two guys in the decays of kaons, which are mesons of down and anti-strange. So we have C and CP violation. And then during the electroweak era, there is also a departure from thermal equilibrium happening. So we have all the ingredients, yet the standard model fails to explain this asymmetry. The reason is because they're there, but they're not sufficient enough. So we have to think of new models. Anyway, so that's the area where we do our research. We try to come up with models trying to address this. There are two ways to go about it. I'm a theorist, but I have mentioned some experiments. One is that we study antimatter better. We try to understand the CP violation that is happening in the standard model. We try to understand it much, much more better than the current learning that we have. And for that, we have some experiments. For example, we have something called as Antiproton Decelerator. Just as a particle accelerator accelerates particle, giving them kicks, I mean energy boost, the purpose of a decelerator is to slow it down. So the idea is that if you have an antiproton, you deaccelerate it, You really slow it down, then using some electromagnetic fields, you try to slow it down and then capture it. And once you have it captured, then you start observing it, what it does, how it interacts. So we learn more about what antimatter actually is. The second experiment is LHCb. LHCb, you can see the flipped sign which they have in their logo as well, trying to differentiate between B and B bar. So they study how antiparticles travel and transform in motion in the detector. So you generate them in the collisions and you see their tracks, you see the particle tracks, and then you try to understand, okay, how are they behaving, how they are traveling. And these two experiments, so yeah, if we learn more about the properties, maybe we get to know something that is not predicted by the standard model, something else that we are missing and we don't see right now. So that's the aim of these experiments. The third one, AMS, or the alpha magnetic spectrometer, is looking for antiparticle regions in space. That's why I said I'll get back. So we haven't ruled out the possibility that, okay, there could be regions of antimatter existing out there. It's just that it's looking for them and it has found no signals. For a much, there are no fluxes and no signals, but they are working on it. They're looking for regions. If they see that, okay, if there are regions of antimatter, maybe we would see some sort of annihilation signals or a flux that we can observe. So that's the AMS. From a theoretical point of view, what we need to do is we have to go beyond the standard model. So together, dark matter, neutrinos, and the baryon asymmetry are all these beyond standard model physics problems, where we believe that the standard model is just a low energy manifestation of some high scale theory. The high scale theory can provide explanations about several other problems, including the baryon asymmetry. The problem is that since they're high scale and we're also doing physics of the early universe, they are very difficult to probe and are beyond the current reach of our experiments. So the goal and the direction in which we are working is to come up with mechanisms that you can probe at low energy scales and that may also be probed in the near future experiments. And that was all. Thank you.
Thank you for the talk. Before questions, please don't leave after questions because Galoto has to say something from the activities of this afternoon. So please don't leave after the questions.
Hello.
Yeah, hi.
Really nice talk. I really enjoyed it. And this is part of my curiosity, again, not my background in the research. But as you mentioned, we have electron and positron as a matter and antimatter particles. So if we put them side by side, they would interact with each other and let's say their momentum would increase even before interaction. So their energy is increasing, right? Like theoretically, if we put them side by side in the near.
No, I don't understand what you mean by putting them side by side, because these are particles which we're talking about and the description is different. I mean, when you go to theory, the description is we work in terms of fields. So I don't understand what exactly you mean by side, but the idea is that if they come near to each other,
yes,
they're just going to annihilate.
Yes, so just before they annihilate each other, so their momentum would be increasing, right? As they are.
Okay, of course they're getting attracted. This is
Yes.
positive and negative, so they're getting accelerated towards each other. This
Exactly.
is electromagnetic interaction between them.
Yes, so just same way, if we put particles, as you mentioned, there are also for without this charge property.
Mm-hmm.
So how do they interact, like theoretically?
So there is another property that I called about the parity. Remember, like they have other properties like spin and handedness. For example, the neutrinos, they don't carry any charge, but we can then distinguish depending. Okay, they're left-handed, right-handed, and so on.
Yeah, but theoretically, has it been predicted that just like this electron and positron, will there be attraction between this without charged particles, or it's not been done yet, or something?
Okay, so you're asking if there will be an attraction between a neutrino and an anti-neutrino when
Yes.
they come in together.
Yes, because of some other force that we might not even think
No,
about
no, neutrinos interact only via the weak force, so they'll come in together, and then also they come in with pairs. With the, if you go, let me go back to here. So the neutrinos come in generations. They always come. They are like different types. You have the electron neutrino, muon neutrino, and tau neutrino, and they're always usually produced in combination with the lepton family they belong to. So they have this as a scattering which goes on. I think if you look at the process, it would be like, okay, something goes in. For example, if simply take beta decay, P going to N, or plus E, some antineutrino. So they're always produced in combination with the charged particle or the lepton family they belong to.
Of course, that is the practical view. I'm just talking about theoretically. If we put them just on the paper, does it? Has anyone done any calculation?
I don't have an idea about it, really. If they have done it on paper regarding this or not.
Okay. I guess. Yeah. I guess.
I mean, when we talk about interactions, is when these particles that we have a different treatment, it's not as the classical one, when they meet. So you don't, it's like you can consider that the times are short enough that we don't have this difference in the momentum of the particles, if this is your question. But when we are talking interaction is when they meet. So we don't care if they've been attracted or not. The only thing that you take into account is what we call the cross-section, and is the probability to interact. So it's not that they attract one to the other.
My question was, if they attract to each other, what force could it be? If it is not just
Gravitational is the only one, but they are so light that they don't.
Yeah.
No, but you have to think this like those particles, they find one to the other, and they have a probability to interact. I mean, they can like make this collision, and they can. You have the probability that they don't interact, but this probability is given by the weak force.
As I said, like they interact mostly by weak force, and as Danny mentioned that. We talk everything in terms of probabilities. You know, something happening, we talk in terms of cross-section. Is the chance whether this meets this? We calculate it from our theory, and that's how we get it. So that's why when you say, okay, can we put them side by side? I can't say anything. You know, not even theoretically. I mean, it's undeterministic over here, because how can you put it side by side? So that was my point. But yeah. There could be, regarding other forces, yeah, people are trying to think that, okay, there could be some new force or something, but we don't know, because as far as we know, the neutrinos, they interact via the weak force. Here, okay, okay.
Yeah. And we said that we have observed the 10 to the minus 10 asymmetry. How did we observe that?
How did we observe it? Good question. I did not include it for technicality reasons. Okay, there are several observations that indicate this. You have this band that you see over here. This is called the cosmic microwave background radiation, CMBR. So we have a model of cosmology that we call the lambda CDM model of cosmology. It talks about how different structures formed, and so and before that, okay, we also have when these particles form this process called Big Bang nucleosynthesis. Together from these processes, we calculate densities of different particles, for example, for photons and baryons, and that's how we get to observe. So this is more technical part, which I did not include in the talk. But from cosmic microwave background radiation and Big Bang nucleosynthesis, you get the same results, that the baryon asymmetry is of the order of 10 power minus 10.
Okay, so you just observe the microwave radiation.
Yes, and also this, when the particles form, when the nucleons start forming, for the Big Bang nucleosynthesis, you observe the abundances of the light elements, for example, hydrogen, helium, lithium, and then you see, okay, you compare the abundances. Okay, of course you don't see anti-hydrogen or anti-helium and so on, and then you compare, and then you get an estimate.
Okay, thanks.
Someone from there.
Okay, 2 questions.
Hello, thank you for the talk. And maybe actually it's
quite related to the question that you just answered. That is, like, I was wondering, maybe you said it also, that why baryon, you expect the baryon asymmetry to happen at that moment, right? It's just before the
this assumption that what if it started asymmetric?
No, I mean, it started symmetric, and then the asymmetry happens. You said it right in the before or after.
Yeah.
Like why after? I guess it's just what you just answered.
Oh yeah. That's what my point was. That okay, the mechanism comes into play. Okay, we start, and then the mechanism starts differentiating that we need to probe. I mean, the CPU violation, and that generates the excess. I don't know if this was exactly the question or what. Okay. Yeah. So then you see the particles. Oh, let me go back to this again. Yeah. So the particles start forming over here, and before that, if things are being produced asymmetric, then the annihilation should have taken place, and of course there was some mechanism which differentiated. So at the end, the baryon-anti-baryon pair annihilation takes place. We are left only with baryons, which start coming in together like nucleosynthesis, and they start forming nucleons, atoms, and so on. There is one there.
Thank you for the talk. I was wondering, could dark matter explain in some way the baryon asymmetry at the start of the universe? Like we haven't observed it reacts with matter, but maybe it reacts with antimatter, but it's so.
Okay, yeah. Thank you for pointing this out, because this is the actual area of my research on what I work. So I work on something called as asymmetric dark matter, which means that the dark matter also has asymmetry, and there could be, for instance, just like the baryon abundance, what we see is set by the baryon asymmetry. We believe that the dark matter abundance could be set by the dark matter asymmetry. And then we need to think of processes. I mean, what happens is that maybe the asymmetry from one sector is getting transferred into another sector. For instance, let's say I have an asymmetric dark sector, like you said. We have an asymmetry there. I have some interactions which couple the dark sector to the standard model. For example, these are called portals, which Leo mentioned in his talk, which connect the two sectors. So we could have some interactions which connect the two sectors, which transfer the asymmetry in the dark sector to the visible sector. Or it could be vice versa. The asymmetry in the visible sector gets transferred to the dark sector. Or there is some mechanism which generates the asymmetry simultaneously in both the sectors. So this is what I work on. But yeah, you're right. We could have in principle asymmetric dark matter and then asymmetry there, which could in turn generate an asymmetry in the baryonic sector that we observe. So yeah, you're right.
Okay, thank you.
Okay. Any other questions? I don't see. Okay, so I have one question for you.
Yeah.
You were talking about this, the generation of this asymmetry. How can you, because in the standard model, you don't have enough asymmetry generated.
Exactly.
So how can you generate more asymmetry beyond the standard model? If you can give us any examples of that.
How can I generate? You want a BSM example of asymmetry generation? Or okay. So one thing that again I work on is something that we call leptogenesis. So I go back to the standard model. I showed you, okay, these are baryons, and these are leptons. Now in leptogenesis is one such model, because we've talked about neutrinos. The neutrinos in the standard model do not have mass, but we have observed neutrino oscillations which suggest that the neutrinos have tiny masses. So what is generating these tiny masses? Because there is no right-handed neutrino. Okay, if you look at the standard model, you have right-handed and left-handed terms which give the mass term, but for neutrinos there is no right-handed term. And so one of the BSM scenarios is we add right-handed neutrinos. These right-handed neutrinos, there's this mechanism called seesaw mechanism, which gives very tiny masses to the neutrino. So the heavier your right-handed neutrino, the smaller your light neutrino masses. These same right-handed neutrinos that you add to the standard model, they also violate lepton number. So as I said, this is again one of the first condition was that the baryon number should be violated. This was for baryogenesis. Let's say I'm generating an asymmetry in the leptonic sector, so it's leptogenesis, so I need the lepton number to be violated. And these right-handed neutrinos, they do violate that lepton number. So the decays of these right-handed neutrinos, if they prefer, okay, if they decay to, let's say, a lepton and a scalar, and they prefer the lepton over the anti-lepton, I can generate an asymmetry. So I get an asymmetry in the leptonic sector, and then I go back again to the processes, these fast processes in early universe, which I did not tell the name. These are called as phalerons. So we have these phaleron processes which conserve B minus L, but they violate B plus L. So these phaleron interactions, what they will do is they will reprocess the lepton asymmetry into a baryon asymmetry. So this is one of the most famous examples of BSM models that can generate this asymmetry. And the beauty is that it explains neutrino masses, oscillations, and baryon asymmetry all together in one go.
Thank you again for your talk, and now I'll leave the microphone to Galoto so she can explain you.
Okay, so as you know, this afternoon we have the social activities. So first we will have a leisure activity here in this room. It begins at 4, and if any one of you is interested, it will be kind of a contest just to have fun. You're obviously all invited. And then there's the guided visit through Valencia. It will start at 6:45 in La Llotja de la Seda. If you want, you can go by yourselves using Google Maps or whatever. But if you don't want to go alone, I will be leaving from here using public transport, the tube. Also, the tube leaves at 6. So if you already have a ticket, you can meet me at 6 in the train station that you can find at the door of the campus. And if you don't have a ticket, please come beforehand and I can help you buy one or whatever you need. And then there's the dinner, which you should have already signed up for. If you haven't, you can't come now because we had to talk with the restaurant because we are a big group. So yeah, that's all. If anyone has any questions. So I'm not sure because we will be walking through the historical center of the city, but I'd say 1 hour, more or less. Around 8. Where? In Torres de Serranos. Okay then, until 9 o'clock.